Welcome back, everyone, to part 38 of our lecture series entitled Math 1210, Calculus 1 for students at Southern Utah University. As usual, I'm your professor, Dr. Andrew Missledine. It's great to have you all here today. So this lecture 38 here is entitled Autobots, Roll Out. I know it's a horrible pun here, but I'm going with it anyways. Today we're going to talk about optimization problems. Optimization represents one of the capstone topics when studying. In the previous lectures, we had talked about curve sketching on how the shape of the function is determined by the derivative and second derivative, which really brings all of these ideas that we've learned about derivatives together. Optimization is very similar in that nature, that it brings in together all of what we've learned about derivatives, but also some other cool aspects from pre-calculus type problems. The methods we've learned for finding extreme values have practical applications in many areas of life. A business person, for example, might want to minimize cost and maximize profit. A traveler who wants to minimize transportation time will try to, find the path of shortest distance. As another example, Fermat's principle in optics states that light follows the path that takes the least amount of time. And so optimization problems, I'm just from these examples just trying to say that they're everywhere. In this section, that is, this lecture is based upon section 4.7, optimization problems from James Stewart's calculus textbook. And in this section, we're going to be looking at lots of problems about maximizing area, maximizing volume, maximizing profits. Sometimes we want to minimize, though, minimize distance, minimize time, minimize cost. Use this gender neutral term of optimization. What is the optimal answer? What's the best answer? Well, sometimes that means maximizing, sometimes it means minimizing. But minimize our answers. It turns out that we have the following basic strategy that we're going to go. So what are the ingredients? Well, not the ingredients. What is the instructions for an optimization problem? We'll think of it as like a recipe that we want to bake in our kitchen here. What are the step-by-step things that we need to do? Well, it probably goes without saying, but I'm going to say it anyways, because whenever someone says it goes without saying, they end up saying whatever it is that goes without saying. But when it comes to any story problems, optimization problems included, the very first thing you need to do is read the question. I can't emphasize enough how important that is, because sometimes we're just so used to problems falling in various templates, we just jump in without even knowing what's going on. And so in particular, we need to read the problem, and we need to read the problem carefully. Reading a math problem is not the same way as reading Harry Potter. You might need to take your time to make sure we understand exactly what's going on here. The story problem is going to be expressing quantities that are related to each other. Some of them will be known quantities, they're given to you. Some of them are going to be unknown. It's helpful to figure out what is it that we want to figure out and what is given. So determine what those things are. The next step, it's sort of an optional step, but I recommend it highly here. If all possible, draw a picture of what it is you're trying to solve the problem, especially for this section in the textbook. All of the examples are very much geometric in nature, so they lead themselves very naturally to drawing pictures. And this can be difficult in other situations, but feel free to draw a picture to help you understand. And in particular, one of the advantages of the picture is so that we can label it, specify what things are. Are these dimensions of a triangle, of a cube, of a rectangle, what have you? And so, although as we're trying to optimize a variable, so we have to decide which variable. And sometimes when I say decide, sometimes it means we have to determine what variable to optimize, whether that's a max or a min. It doesn't matter. It depends on the context. We have to figure out which variable. When I say decide, it's because we get to pick the variables' names. So if we came up with a bunch of variables X, Y, and Z, which one are we trying to optimize? Like, oh yeah, we're given information about X and given some information about Y. We want to optimize Y. Okay, we'll do that. And for these situations, for this section 4.7, each of these can be written. We can come up with an optimizing function. an optimizing function. This is our function f of equals, well, there could be lots of variables, x, y, z, etc. We're trying to optimize this guy right here, f of this. Now, this is single variable calculus. We're not going to be having a lot of variables floating around here. In particular, can we write this optimizing function as one variable? And sometimes that's not going to be exactly obvious how to do that. The way that we're going to do that is we're going to have something called a constraint. We don't need that article there, but constraints are going to help us out here a lot. Constraints are a big part of optimization problems because we can't just type in our favorite cheat code like show me the money or glittering treasures or whatever other video games you like to play, right? We don't just have infinite resources. There's some type of constraint, some restriction on what has to happen. We don't just have infinite money, therefore we can't just produce infinite many commodities and sell them all to make infinite profit. There's a limitation, whether that's time or money or other constraints. Constraints will help us relate variables together. And so we'll mostly be using constraints to help us get a single variable function that we want to optimize here. Once we have our function in hand, it is important to recognize the domain of the function. Again, this has to do with things like constraint and other realistic situations. Does negative even make sense for the situation? Like, can our input variables be negative? If that's time, maybe, because it means that something happened prior to the start of the experiment, but typically that means a no. And so you determine what type of things are acceptable. Are the answers real numbers? Are they rational numbers? Are they integers? Integer optimization becomes a very fundamentally different problem than real optimization, the type of things we're going to see here. That is, we'll allow for decimals. Right. So once we've identified the domain, then we're going to be looking for the critical numbers of the function, which means we're going to have to be looking for f prime of x when it's equal to 0, or when it doesn't, when it's undefined, d and e. Again, but typically, though, the D and E apply to an optimization problem because we have to choose input that are realistic. And so if the function's undefined for certain values, it doesn't matter if that's optimal. We can't pick something for which makes our function undefined. So we're typically going to be looking for what makes our optimizing derivative go to 0. Find those critical numbers. And then because most of the time this is going to be a closed, the type of examples we're going to see. Because of the domain, there's some fixed values, a, b. Like, we can't get less than a or bigger than b in this situation. And so because of that, we have these extreme value problems we've seen before, where we look at a, we look at b, we look at any critical number that's in between them. And so we might get something like the following. It's like, okay, the maximum happens right here. And so we're looking for those things as well. Now, if the domain is open, it is possible to still find an optimal solution, because after all, if you have a cost function, we're trying to minimize cost. Well, admittedly, there's nothing that stops us from just producing more and more and more and more and more commodities in our factory, which would increase the cost. I mean, admittedly, we're not going to be able to produce infinite amount in a day, but if we sort of idealize, well, is there any restriction? No, not really. We can still find solutions. It should be the case that a cost function has a minimum. It should be that a profit function has a maximum and things like that. So a lot of this will make much more sense in context. So what I want to spend the rest of our video here is actually going through some specific examples. And like I said, most of these examples are either directly from James Stewart's calculus textbook or modifications of those. And so imagine as our first one, this is like the classic example. One cannot learn optimization without figuring out how to build a fence for which one side is missing. So what do I mean by that? So imagine we have a farmer. And the farmer has 400 feet of fencing and wants to fence off a rectangular field that borders a straight river. So let's kind of draw the picture right here. We have our river going on right here. Rivers are typically blue, so that's the color I'm going to do it. And so we're going to make a rectangular fence that is next to the river like this. And so the farmer doesn't have to put any fencing along the river because the river acts as a natural barrier between his property and the neighboring property. And also, if we're gonna like maybe keep some animals inside of the fenced area, then well, maybe we don't want to fence by the river so that they can go get a drink or whatever. Whatever the reasons doesn't matter. The point here is that we have a rectangle that we're trying to build, and it has already built into it, and therefore we only have to put 3 sides of the rectangle. And so what dimensions of the field have the largest area? So this is the key word right here, largest. That word right there is an optimal type of word. We are trying to maximize the area, of this field. All right, so how does one maximize the area of any, or in this case, how do we optimize the area of this field? Well, it is a rectangle, and so the area of a rectangle is going to equal length times width. Let's say that the short side here, we're going to call that x, and x. And then the long side, we're going to call it y. And admittedly, I shouldn't call them long or short because we don't know which side is going to be bigger. I just drew a picture of what it could look like. But we'll say it runs parallel to the river, has length y, and the 2 other sides that run perpendicular to the river have width x. In that situation, the area is going to equal x times y. And so our optimizing function here, because every optimization problem has an optimizing function. This is the thing we're trying to optimize. Our function is this a equals x times y. All right. But like I warned you about before, this is our function actually is it has 2 variables, x and y. How do we deal with these 2 variables? How do we work in the presence of 2 variables? Well, that's where this 2,400 feet comes into play right here. This 2,400 feet of fencing is our constraint. Every optimization problem has a constraint. We don't just have infinite resources. Because if the farmer had an infinite amount of fencing, he can make a field that's infinite in size. But the fact that our farmer is stuck with the 2,400 feet, that so what does that mean? So what we have is that the perimeter of this rectangle is going to be the 2,400 feet. But how does this perimeter relate to the variables present? Well, if you think about our rectangle, we have one x, we have a y, and then we have another x. We don't have a second y because of the river there. And the perimeter is then going to equal 2x plus y. The perimeter of a usual rectangle will be 2x plus 2y. We only get 2x plus y. And so if we use this constraint, we can solve for one of the variables. Let's say we try to solve for y right here. Y would then equal 2,400 minus 2x, for which we can then plug that into the optimizing function for the variable y. And if we do that, then our optimizing function turns into the following. A equals x times 2,400 minus 2x. And I'm going to distribute this thing through because my ultimate goal is to be taking a derivative. And although I could use the product rule, it's going to be a little bit cleaner if you distribute the x. So we get 2,400x minus 2x squared. Right? This is our optimizing function. So now, so some things we could think about now is that in terms of domain, what are the domain right here? And so thinking of our river one more time here, we have our river right here. What can we have for our x's and y's? Well, in terms of x, the smallest x would be like 0. If your x was 0, then your river, or not your river, your fence would just be all the y. That would be like y equals 2,400 feet. And it would be like we built a wall next to the river. Clearly, this is not going to be a good choice. At least from a geometric point of view, it seems ridiculous. Try to build a sign chart, not a sign chart, a t-chart, where we have x and a right here. If you set x to be 0, your area is going to be 0 as well. That's going to be ridiculous. Clearly, that's not going to be the maximum area but it is part of the domain, so it is worth considering. Sometimes at the boundary. On the other extreme, what if we put all of the fencing into the X and not into the Y whatsoever? If we did that, we'd have a fence that goes down, and then we have a fence that comes back, where the thickness between them is nothing. In that situation, we would have the 2400 equals 2x, because y is 0 in that situation. So x equals 1200. Again, that kind of seems silly, but again, that's the situation we have right here. If we put everything into the x, you're likewise going to get 0 area. This gives us the domain of the function, 0 to 1200. And even if these are absurd answers, it is important we know the domain, because as we go searching for critical numbers, we have to disregard any critical number that's domain. All right, so let's find the critical numbers. We're going to take the derivative of the area with respect to x. And by the usual derivative rules, a prime will equal 2400 minus 4x. And we want this to equal 0. Adding 4x to both sides, we get 2400 equals 4x. And divide both sides by 4. We get x equals 2400 over 4. 4, of course, goes into 24 6 times, and so we end up with 600 feet as this single critical number. And so this is our only critical number. Given the other two were 0, I have high hopes that this number will hopefully be something better. And so if we go back to the original function, a equals x times y, if you want to, you could plug the 600 in to this equation right here. And so you get something like 2400 times 600 minus 2 times 600 squared. That's going to be nice and dandy. The arithmetic's a little bit more complicated here, not too much though. On the other hand, though, if we just think of the x and y situation right here, if x is 600, what is y going to be? Well, like we saw before, y was equal to 2400 minus 2x. And so you're going to get the 2400 minus 2x, which is 1200. You end up with 600 times the 1200. And so whichever one you do, these are going to be the same thing. You're going to end up with 720,000 square feet. I never mentioned this here, but we were looking for area, so these are all going to be square feet. And so by the extreme value theorem we've seen before, there has to be an optimal solution in this closed interval, and it's going to either be at the boundary or a critical number. And so we see right here that the optimal solution is going to be right here. And so if we record what we find here, the maximum area, well, it's going to be 720,000 square feet. Now, remember, the original question didn't actually ask what was the maximum area. What it asked is what dimensions will give us the maximum area. So make sure we actually answer the question that's given. And so the maximum area is going to be 720,000, and it's obtained at a 600 by 1200 feet. 600 feet by 1200 feet rectangle. And so what will often happen when we work with these optimization questions here is oftentimes there is a unique critical number, like we saw right here. That's not always the case, but that happens a lot for these type of textbook examples here. And oftentimes, because there's a single critical number, you get that the optimal solution will be at that critical number. I don't want you to jump the gun, though, and just to automatically assume that because you have a single critical number, it is automatically the best answer. We'll see some examples later on for which the critical numbers might not be the best answer. It could actually happen at the boundary. We'll hear. So this one is a purely number theoretic situation here. Find two non-negative integers x and y for which 2x plus y equals 30 such that x, y squared is maximized. So this right here is what we're trying to optimize. I mean, using the words like maximize, that's clear what we're trying to do. Let's take let's take the value z equals xy squared. We're trying to optimize the value z right here. This is our optimizing function. But it has two variables. We have x and y. Much like the previous example, we need to find some way of removing one of the variables. And that's where this constraint comes into play. The numbers must be chosen so that 2x plus y equals 30. Because if we didn't have any restriction on x and y, why not just pick x bigger, 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 y bigger, 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 bigger? There's some constraint between the values here. Now, much like the perimeter one before, I mean, this is very similar like the perimeter situation we had. 2x plus y equals some specific number. For one of the variables, y equals 30 minus 2x. And then we substitute that in above, right here. And so we're going to get that z equals x times 30 minus 2x. And this is squared. And so we want to maximize this value. So even though our optimizing function is now xy squared as opposed to xy, and our so quote-unquote perimeter function is a little bit different, there's different language on this problem. The basic concept is the same. We want to optimize a function of two variables. We use the constraint to remove one of the variables so that our function that we have to optimize is a single variable, and then we're going to take its derivative. Now, in terms of the derivative, if you want to, we can multiply this thing. Because of the squaring here, you have to FOIL it before you multiply things out. I think I might just live with the factorization here, and I'm just going to take the derivative using the product rule. So take the derivative of x, you get a 1. That'll then give you 30 minus 2x squared, the derivative of the other function, plus x times, take the derivative of the square, we get 2 times 30 minus 2x raised to the first, and then times it by the inner derivative for the chain rule. We get negative 2 there. Let's clean that thing up a little bit. Some things to notice. That the first term, the 30 minus 2x squared, showed up, but also the next thing had a 30 minus 2x in it as well. We could factor that out. Actually, the main reason I didn't want to multiply out I didn't want to FOIL out the original expression is because there was a repeated factor. I actually knew that repeated factor was going to be useful as I try to factor the derivative using the product rule. So I actually could find one of the critical numbers faster. All right. So if you factor out the 30 minus 2x, what's left behind? Well, you get 30 minus 2x from the first product. Then you're going to get a negative 4x because we had a 2 and we had a negative 2 right there. And so let's see, 30 minus 2x, both 30 and 2 are divisible by 2. You can factor out a 2, leaving 15 minus x. And then let's see, if you take the negative 2x minus 4x, that gives you negative 6x. And then 6 and 30 also have a common factor of 6. If you factor that out, that'll leave behind 5 minus x, like so. And so let's clean that up a little bit more. We get this factor of 12 in front. That won't be too consequential for us. 15 minus x. And then likewise, we're going to get 5 minus x, like so. And this should equal 0, because again, we're looking for critical numbers in this situation. Before we start looking at the critical numbers aren't too hard to find at this moment. We're going to get x equals 15. And we're going to get x equals 5. We should at some point think about the domain of this thing. This has a lot more to do with the constraint than anything else here. Because remember, the constraint said that 2x plus y equals 30. And the original expression did say x and y have to be non-negative numbers. So they have to be greater than or equal to 0. So in terms of domain, x has to be greater than 0. But y, in order for y to be greater than 0, well, like we saw before, y equals 30 minus 2x. Clearly, as x gets bigger, y will eventually get, when does this thing equal 0? That happens when x equals 15. So the domain of this thing will be from 0 to 15. And you'll notice that 15 was one of our critical numbers. So like we said before, it's certainly very possible that the endpoints of the domain could be the maximum values. We have one endpoint at 0, another endpoint at 15. It also is a critical number. And then we had a critical number at 5. So my intuition is going to be that x equals 5 is the best choice. But again, that's often what happens. We have this single critical number. But illustrate what's going on right here. If you plug in x equals 0 into the function, you're going to get 0 times, well, whatever, y squared. That's going to equal 0. And then 15 down here, you're going to get 15. But remember, y is going to equal 0 when x is 15. And so this likewise gives us 0. So as often happens, the endpoints give us an optimal solution if we were trying to minimize area. Or we want to maximize this thing. So to maximize, we get 5 times 30 minus 10 is what we get for y this time, so 20. So we get 5 times 20 squared, 400. And so then we end up with 2,000 as the corresponding z value for x equals 5. And that's going to be our optimal solution here. So notice if x equals 5 and y equals 20, so these are non-negative integers, so that 2x plus y equals 30, then xy squared equals 2,000 is maximal. It's always a good idea with a story problem to finish it up with a sentence. It's a story problem, it should have a story solution. And we're just trying to be very careful that we are finding exactly what we're looking for here. All right, this next example is going to be a purely geometric situation, but it certainly doesn't have to be so geometric here. This idea in this question here was going to minimize distance. So imagine you have a parabola, y squared equals 2x. Now, you'll notice I'm actually squaring the y and not the x. And so this is going to go as a concave right parabola here. And we want to find the point on the parabola which is closest to the point 1, 4, which is not on the parabola. So on the picture, you can kind of see an estimate of where that closest point might be. And so if we're looking for a point that's closest to the point, what we're trying to do here is we're trying to minimize distance. And so if you're trying to minimize distance, we're going to have to use the distance formula in order to make that work. So the general distance formula, you're going to take x2 minus x1 squared plus y2 minus y1 squared. And this all sits inside of the square root right here. Well, one of the points is fixed. It's the point 1 comma 4. So really, we're looking at x minus 1 squared plus y minus 4 squared. And we go from there. And so this is the distance we're trying to minimize. Now, at the moment, it has the two variables x and y. We'll come back to that in just a second. But a very useful trick that comes into play when one tries to deal with minimizing distance, because the distance formula is kind of complicated in terms of derivatives because of the square root and the necessary. What often one can do is if you square both sides, you look at the distance squared. This removes the square root on the right-hand side, so you just get x minus 1 squared plus y minus 4 squared. And this is often more preferable because in order to minimize distance, you can accomplish this at the same time if you try to minimize distance squared. And that is, you can find the minimal distance implicitly. This leads to a much easier drawing. All right, but we're still stuck with the situation that we have two variables, x and y. How do we get rid of them? Well, we need a constraint. What is the constraint in this situation? It's the parabola itself. Y equals x squared. Because after all, the point has to be a point on the parabola. And so we use the parabola as the constraint. You have y squared equals 2x. Think about the forthcoming derivative. You'd get y equals the square root of 2x. We don't want square roots in our derivative if we can avoid it. On the other hand, if you divide both sides by 2, you get x equals y squared over 2. And that's going to be a much simpler calculation in terms of the derivative. So we're going to make that substitution in for x right here. All right, so let's y squared is equal to y squared over 2 minus 1 squared plus y minus 1, sorry, minus 4 squared. So now this thing is prepped for taking derivatives. If we take the derivative, you're going to end up with a 2d d prime equals, let's see, by the chain rule, you're going to get 2 times y squared over 2 minus 1. Then don't forget the inner derivative, for which case you're just going to get a y. And then add to that 2 times y minus 4. And this should all equal 0. Now, if you look at the left-hand side, we have that 2d d prime equals 0. Well, okay. Well, if a product of things equals 0, it's because one of the factors was 0. Well, what's factor? Well, it's not 2. 2 doesn't equal 0, so that's not the culprit. Could it be d? D is the distance. Is the distance equal to 0? Well, like we saw above, the d equals 0 would mean that 1.4 lived on the parabola. But you can check that it doesn't happen. Y squared gives you 16, and 2 times x gives you 2. That's not a solution. Distance does not equal 0 in this context. So the only way that this product equals 0 is if d prime equals 0. And that was the justification why we can work with distance squared instead of just distance. All right, so what do we have here? Distribute and multiply things out a little bit. We will end up with a y squared. Oops. Let's switch it back to white. We get a y squared, actually y cubed, minus 2y plus 2y minus 8 equals 0. You can see that the y's cancel out, and we're left with y squared minus 8. Y cubed, excuse me, minus 8 equals 0. Solving for y cubed, we get y cubed equals 8. And taking the cube root, we'll get y equals 2, the cube root of 8. Now, this is our critical number. And so seems like high hopes that this will give us the closest point. And if we come back up to the picture we had before, y equals 2 right here, that kind of seems to be about where we put this thing. Again, this was just an estimate of where it is, but it seems like y should equal 2. But what would the x coordinate be? Well, if you come to the parabola, when y equals 2, you can get 2 squared equals 2x. So you get 4 equals 2x. Divide by 2, x equals 2. And that seems to be the point. 2 comma 2 seems to be the best point there. In terms of domain, though, what would the domain of this thing be? Like, how close or how far can we get? Well, if you follow down this trajectory down here, you can get arbitrarily farther and farther and farther away. Turns out if you go down this path, the distance from 1, 4 is going to go to infinity. That's not the minimum distance. But if we go down the other trajectory, go farther and farther and farther away, same issue, we're going to get farther and farther and farther away from this point, and that can get arbitrarily large going to infinity as well. So it would appear that our single critical number actually gives us our closest point. 2 comma 2 is the closest point on the parabola to the point 1 comma 4. And so we can minimize distance much in the same way as we try to... for this video, let's look at one last example here. Let's find the area of the largest rectangle that can be inscribed in a semicircle of radius r. So we're not going to specify the radius of this circle here. Let's call it r. And let's inscribe a rectangle. So what we mean by inscribe is that the 2 vertices on the top right here and here are going to live on side of this semicircle. And we want this to be the biggest area possible. So largest area, we're going to maximize area here. Well, how are we going to do it? Well, if we approach it like we did before, we could say that Well, using the coordinate system that we have right here, if the distance from the x along the x-axis from the origin to this point right here, that would be x, and the distance above would be y, thus giving this the coordinate we have right here. If we used x and y right here, our area is going to equal 2x times y. Because after all, x is the distance from the y-axis to this point. We need to have the entire distance right here. So that's a 2x times y. And so one could try to then optimize like we did before. We have this 2x and y. Well, we'd have to remove one of the variables from the other. We could use the semicircle because the semicircle this time actually is giving us the constraint. Now the semicircle as a constraint has the equation, well, just for a general circle, of course, you're going to get x squared plus y squared equals r squared. If you solve for y and choose the upper semicircle, you're going to get r squared minus x squared all inside of the square root. And so then your optimizing equation would look like a equals 2x times the square root of r squared minus x squared. And so we could take the derivative of that thing, but that thing's going to look ugly. I mean, with the product rule, which is going to be necessary, and then the chain rule inside the square root, that's not the most ideal way of optimizing this one. I want to provide an alternative approach that one could take. And this one actually utilizes a little trigonometry. What if we, instead of using x and y, think of the angle theta formed between the x-axis and this point, which is a vertex or the rectangle? Well, then as angle fluctuates, this point could move all the way up to here, or it could move all the way down to here. This kind of gives it the extremes. So this would suggest that theta could be anywhere from 0 to, we'll work in radians here, pi halves. This gives us the domain of the problem. And both of these situations do seem absurd because when you take theta equals 0, theta equals 0 would look like this rectangle right here. It would just be completely flat. Its area is going to be 0. So clearly that's not going to be our optimal one, but for completeness sake, we'll include it. And then the other one happened at pi halves, which similar things happening there. If we take the rectangle at pi halves, it would just be a line again. Like so, its area would be 0. So who's the one in the middle? Let's take a look at that. Well, if we make the appropriate substitutions using some trigonometry here, instead of saying x and y, we would get r cosine theta, comma, r sine theta. For those to kind of give an explanation of how we're approaching this one, we're using some trigonometry to help us out, but later on in Calc 2 particularly, also Calc 3, this technique we're using right now is we're switching from Cartesian coordinates to polar coordinates. The polar solution is much easier, or the polar problem is much easier than the Cartesian problem. If that doesn't make any sense to you, don't worry about that. That's a topic for another semester. And so our area function, if we take 2x, that gives us 2r cosine theta. And if we take y, that's r sine theta. We can rewrite this as 2r squared cosine theta sine theta. And we can then take the derivative here. You notice there's only one variable in the situation now. We could take the derivative. It's not so bad with the product rule, but my trig identity sense is tingling here. 2 cosine theta sine theta. My goodness, that's none other than the double angle for sine. So we get r squared times sine of 2 theta. And that's going to be a much cleaner derivative because after all, r squared is just a constant here. It doesn't change. And therefore, a prime is going to equal 2 r squared cosine of 2 theta. What do you know? That's great. And if you set that equal to 0, we'll divide both sides by 2r. You just end up with cosine of 2 theta equals 0. If you don't like the double angle, we could use some angle identity to switch it back. But I'm actually quite happy with this situation. So we have to figure out when does cosine equal 0. Thinking of your standard unit circle diagram. Cosine measures the x-coordinate. So we're looking for when are we on the y-axis. That's going to be at pi halves and 3 pi halves. We only have to find the solutions in a single period, like so. Now you might wonder, like, isn't 3 pi halves outside the domain? Well, notice we solved this for 2 theta. If we divide both sides by 2, we end up with pi fourths, and we're going to get 3 pi fourths, which 3 pi fourths is in the second quadrant. It's outside of our domain, so that one we can remove, and we can get pi halves. This is going to be our optimal solution here. And admittedly, 3 pi halves, the way we interpreted theta, gives us the same answer, so it wasn't wrong to include it. If we take pi halves and put it back into our optimizing function, what's going to happen there? Well, we get, by what we saw right here, you're going to get sine of pi, 2 times pi fourths. 2 times pi fourths is pi halves. Sine of pi halves is 1. So you end up with the area. I'm sorry. Yeah, so pi halves is going to be our optimal angle that we want to use right here. And so let's put to our area function. That's the, yeah, this right, yeah, just put it right here, no big deal. So we're going to get r squared times sine of 2 times pi fourths, which is pi halves right there. And so we end up with r squared as the optimal area. Great. Now, what did the question ask? Did it want to know the optimal area, or did it want to know the dimensions? Find the area of the, okay, so the optimal area is going to be r squared. And it's obtained when the angle is pi fourths. But what if we didn't know the dimensions in terms of x and y? Well, we go back to the relationships we had before. X equals r cosine. So if theta equals pi fourths, we're going to get r times root 2 over 2. And then y, same thing, r times sine theta, we're going to get r root 2 over 2. So our rectangle is going to look like r root 2 by r root 2 over 2. We doubled the x-coordinate because, remember, we doubled that for the original rectangle. So if we want the dimensions, we're going to get this. And then if we wanted the maximal area, that's going to be an r squared. All right, then. So that's going to be it for our lecture today. I did want to do some more examples of optimization because, again, these ones take a while to get through. So stay tuned for video 39. That's going to continue these examples on optimization. But if you liked our video today, or if you wanted to see more of this type of content, please subscribe. And if you have any questions, post them in the comments below. I'll be happy to answer them. And I'll see you next time for some more. Have a great day, everyone. Bye.